derivatives. And so here we are. We're going to learn about partial differentiation. And if you get a hold of the basic idea, the basic premise behind it, it's not difficult, right? It's just it's organizational, right? You have to keep track of your movements, otherwise you kind of lose sight of things. All right. So a partial derivative is really just taking the derivative of a two-variable function or multivariable function by treating all but one of the variables as constant. Right? So we're gonna pretend that one of the variables is constant, and then we can take the derivative in terms of the other one. Right? So the notation is to use this delta. So you look down here where it says compute the delta f delta x. That's partial derivative of function f of x comma y in terms of x. So what that's saying, because it's in terms of x, we hold y constant. And differentiate in terms of x. So we hold y constant and we differentiate in terms of x. It only starts getting a little spicier when you get into the second derivative, because we call them second order partials. So this would be the first order partial. Second order partials can go a bunch of different ways because it's kind of like heads or tails. If you flip a coin, once, it's either heads or tails, right? So in this case, it's either differentiate with respect to x or differentiate with respect to y. But if you flip a coin 2 times, it could be heads, 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 tails, tails, heads, or tails, tails. So that would be like saying, okay, I differentiate with respect to x, then I differentiate with respect to x again, or I differentiate with respect to x and follow that up by taking the derivative with respect to y. Right? So x comma y as the order of partials, right? Or it could be, differentiate with respect to y followed by y again, or differentiate with respect to y followed by differentiating with respect to x. Right? So it ends up being 4 different possible second order partial derivatives. So it's exponential order 2 whenever you increase the number of or the step in the derivative. So if I wanted to take the third derivative, there would be 16 possibilities, and then followed by 8 possibilities. Fourth derivative, 16 possibilities, and so on. All right, so 2 to the power of whatever derivative it is. So in this case, we're just starting off. This in Calc 1 would be a pretty beefy problem because you'd be looking at implicit differentiation, not the case here. So what we can do, and there's 2 different forms of notation. So we can do, that's my delta. I mean, as long as you do a funky D, don't make it look like a D, you're good, right? So I don't go looking to take off points on that. So partial with respect to x. Then you can see they kind of start morphing into 2's. I have no control over my deltas. The alternate notation would be to say a lowercase f with a subscript of x. That they mean the same thing, right? Both of them are the first order partial derivative with respect to x. Okay. So any term that's exclusively in terms of x, you're going to differentiate that the way you always did. So that's going to be 6x. This is the next part is the first interesting thing here. Here, let me just make a decent looking rectangle. We're going to treat this as constant. Because we're holding y constant, which means any term that's exclusively made up of y's, no x's, is going to be constant. Derivative of a constant is equal to 0. Right. The next two are a little bit more interesting because when I look at this one here, you know, like I said, in Calc 1, that would be implicit differentiation. But we want to think of this as, negative 2y times x squared. All right, the negative 2y is your constant multiple. The x squared is the variable part of it. You're still applying the power rule. The power rule derivative, it would only be applying to the x squared. Everything else is held constant. So this would be minus 2y times 2x. And the same idea would hold true for the next one. And go purple for the cubic square home. Okay, I didn't put my line draw tool on. All right, I'm going to live with that. We want to think of this one as 7y squared times x. And then we differentiate just the x. Derivative of x is 1 times 7y squared is going to be 7y squared. So 7y squared times 1. The 9 goes to 0 because 9 is the conventional definition of constant. The conventional 3.3. All right, so that would be a partial derivative, which I can clean up and write it as 6x minus 4xy plus 7y squared. And we'll talk about what the meaning is behind partial derivatives as we go, but it's really kind of along the lines of what we were talking about before with limits, different pathways. You know, if you're following an X path or a Y path, you know, what's the rate of change otherwise? So a good way to look at it would be cross sections. If you were to take the XY plane, actually that's a bad example. I want something in terms of X. So the YZ plane, and slice through a solid so that you have a cross section. The edges of that cross section would create a two-dimensional curve. This would give you the slope, the rate of change along that two-dimensional curve. All right, so it's definitely a very visual thing, but if you start kind of thinking of it in terms of cross sections, it tends to help. So number 2 is all 4 second-order partial derivatives for this bad boy. So this is one of those where you just kind of strap up and get ready. But the good news is, I mean, if there is any, we already have the first order partial with respect to x. I'm going to snag that. So I'm going to write this as f lowercase f sub x, the simpler notation. If I'm going to have 4 partials with respect to all the variables, I'm also going to need the first order partial with respect to y. All right. So I'm going to bring this in here, and I'm going to write f sub y. Same idea. Constant. That's going to 0. Differentiate the way you always would because there's no x here. Plus 8y. Okay. Treat the 2x squared as a constant multiplier. And really, you're just taking the derivative of the y portion of it. That looks terrible. You can see the highlighter. You're just taking the derivative of that guy. Derivative of y with respect to y is 1. So this just becomes minus 2x squared. And then for the last bit there, let me box that one in. We're treating the 7x as a constant multiplier of y squared. So we're only differentiating the y squared, which would be 2y. 2y times 7 is 14. Well, 2y times 7x would be 14xy. And the 9 goes to 0 again because it's constant. Right. So then I can look at this and say, all right, well, that's the same as saying f sub y is equal to 8y minus 2x squared plus 14xy. So I have my first order partials. Now I just got to find the derivative of these 2 times a pop. All right, so I'll go back to the f of x, f sub x, and I'll find the second order partial with respect to x. All right, so we got 3 things here, 3 items. It does tend to get easier for polynomial-based functions as you work your way down the line because it tends to reduce in power. Okay, but derivative of 6x with respect to x would be 6. It's not a 6. That's a 6. The derivative of 4xy, negative 4xy with respect to x. So negative 4y is my constant multiplier of x. The derivative of x is just a 1. So negative 4y. 7y squared is constant. It's treated as constant when we're differentiating with respect to x, so I leave it at that. All right. Now, if I wanted to go after this with the second order partial with respect to y, then the 6x goes to 0 because it doesn't have a y in it. Negative 4x would act as a constant multiplier of y, so that would be minus 4x. And now we do get a meaningful derivative for the 7y squared, which would be 14y. All right, so this would end up being equal to negative 4x plus 14y. So I have 2 of the 4 necessary second order partial derivatives. Cool. Just need 2 more. Just going to kind of bring this over here. A little side-by-side action. Draw a little arrow. So I want second order partial. And these are the mixed second order partials, f sub x comma y, f sub y comma x. All right. So when I take the derivative here, again, we have the 3 components, 1, 2, 3. It's with respect to x, so this is going to 0, for quality 0. Negative 4x. And here we're just differentiating the x. Derivative of x is 1. 1 times 14y is 14y. So we get negative 4x plus 14y. All right. Now, if you look at the other mixed second order partial, you notice something hopefully that's very, very pleasing. They're the same. That's great news. All right. If you're dealing with continuous functions, which is why we talk about continuity, and we didn't verify it in this case because we didn't really need to. There's no values excluded for x or y. But if your function is continuous, then its second order mixed partials will be equal to one another. All right. So once you find one, you already have the other. So that's pretty good news. Right. Then we have f sub yy. So an 8. Then we're going to get a 0, so plus 0. And then for that last one there, we're differentiating with respect to y. So y goes to 1, so we'll have a 14x. All right. Oh, it's with respect to y, so the first one's actually an 8. Oopsie daisies. So we're looking at 8 plus 14x. My color coding got messed up, so I'm just fixing it real quick. All right, but those second order mixed partials will be equivalent to one another, so that's good news. So numbers 3 and 4, kind of along the same lines, just a little spicier. I'll put some stars on those bad boys so you can tackle those for next class. And number 5 also, that addresses the equality of mixed second order partials. So, so you can kind of see where that goes. But I wanted to touch on one last thing tonight.